So today we're looking at factorizing polynomials and ways we can factorize polynomials. So if you'll notice with these particular examples, we're looking at cubics, so x cubed. We know how to factorize quadratics, so these strategies are for us to factorize cubics or anything higher than that. So our first key theorem that we're going to be looking at, and we are going to be looking at a few theorems today, is that when p of x, so our polynomial function, is divided by a particular linear factor, the remainder is going to be p of negative alpha over beta. So the beta comes from the number next to the x in the linear factor, so x's coefficient is going to be our beta, and then the alpha is going to be the constant in our linear factor. So let's apply that because I know it doesn't mean anything right now. So our first example, we need to use the remainder theorem to find the value of the remainder when. So looking at our first polynomial, p of x is equal to x cubed minus 3x squared plus 2x plus 6. Okay, now we don't need to factorize it. All it's doing is asking for the remainder. Okay, so what I'm going to do first in this particular example is I'm going to identify my beta and my alpha. So remembering that the beta is the coefficient that goes with x, which in this particular case beta is equal to 1 because the coefficient of x is 1. And our alpha is the constant on the side of our linear factor. So alpha is going to equal negative 2. Now, remembering I need to substitute in negative alpha over beta to figure out what my remainder is going to be when it's divided by this particular factor. So my p of negative 2 over 1, because my alpha is negative 2, my beta is 1. So I'm going to get p of 2 because the negatives are going to cancel out. So I'm going to get a positive, and 2 over 1 is just 2. It's a whole number. So I'm going to substitute p of 2 into my equation. So I'm going to get 2 cubed minus 3, 2 squared plus 2 times 2 plus 6. So figuring all that out, I've got 8 minus 2 squared is 4 times 3 is 12 plus 4 plus 6. So negative 4 plus 4, it's going to be 6. So if I was to go through my whole long division process by dividing that particular polynomial by x minus 2, this is telling me that my remainder would be 6. So when we get to the bottom of it and we have that number left over, that's what my remainder would be. Okay, let's do that again for example B. So with this particular example, my beta is 2. That B looking letter is beta, it's a Greek letter, and alpha is the other letter, by the way. So beta is 2, alpha is equal to 1, positive 1, which means that the p that I'm substituting in is going to be negative 1 over 2. Because neither of them are negative, so nothing's cancelling out that negative in front of the fraction, and then I've got a on top and beta on the bottom. So I'm going to substitute that in. So I've got negative 1 over 2 squared minus 3 times negative 1 over 2 squared plus 2 times negative a half plus 6. And now looking quickly to get that answer, unless anybody feels like typing in their calculator, I'm going to get negative 1 over 8 plus 1 plus 4, which is going to give me 39 over 8. So that would be my remainder. So if you're asked to find the remainder of a particular, if you're dividing by a particular linear factor, you can use this theorem to find the remainder without having to go through the whole long division, if that's what the question's asking you. Okay, example 10. When p of x is equal to x cubed plus 2x plus a, and it's divided by x minus 2, the remainder is 4. So we need to find the value of A. So similar theory, but this time we have the remainder. So we know that beta is equal to 1 and alpha is equal to negative 2. So I'm going to be substituting in P of 2 because negative of negative 2 over 1 is going to be 2. So I'm substituting in 2. So 2 cubed plus 2 times 2 plus A is going to be equal to 4. So solving that all now, I've got 8 plus 4 plus A is equal to 4. So 12 plus A equal to 4. So A is going to be equal to negative 8. So for this particular one, we're making it equal to our remainder because we know we're using our theorem in a different way to solve for A. Questions so far? Okay. Another factor theorem. Basically what this whole big chunk of green is saying is that when I substitute in a value, if it equals 0, it's a perfect factor. So there will be no remainder, it will be a factor. So if you want to find a factor, what you're aiming to do is find a value that you can substitute in that will give you 0, not a number. So as it's saying here, if you substitute in P of alpha, that tells you that x minus alpha is going to be a factor. If you substitute in negative alpha over beta and that equals 0, then it means beta x plus alpha is going to be a factor. Okay, so looking at our next example, we need to show that x plus 1 is a factor of this particular polynomial. Okay, how we're going to show that? So our beta is equal to 1. I'm always starting with beta and alpha when I'm doing this. And my alpha is equal to negative 1. So my alpha is equal to negative 1. So what I'm going to be following here is my P of alpha is equal to, if P of alpha equals 0, then x minus A is a factor. I'm wanting to show that x minus alpha is a factor. So my alpha is negative 1. So I'm going to substitute that into my equation to show that x plus 1 is a factor. So I've got negative 1 cubed minus 4 negative 1 squared plus negative 1 plus 6. So negative 1 cubed is negative 1. Negative 1 squared is positive 1 times 4 is going to be minus 4 minus 1 plus 6. So that is going to give me 0. Negative 1 minus 4 is negative 5, minus another 1 is 6, plus another 6. Sorry, I wrote 6, I meant 0. It's going to give me 0. So this tells me that x plus 1 is a factor. It is a factor because it's given me 0 when I've substituted it in. Cool? Okay, so we need to factorize this now. So we need to find a factor that's going to give us 0. Now, we're going to do the rational root theorem in a second, but if you forget it, that's okay. You can just find a couple of numbers that will get you there. So generally, I always start with 1 and negative 1. They're the easiest ones to start with, and generally I'm not going to be giving you a hard linear factor to be dividing by anyway. So for this particular example, I'm going to start with 1. I'm going to try substituting in 1, see if it gives me the answer. So giving that a go, P of 1, 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. So I've got 1 minus 2 minus 5 plus 6. So 1 minus 2 is -1, minus 5 is -6, plus 6, I'm going to get 0. So this tells me that so therefore x minus 1 is a factor. Because remembering alpha, it's x minus alpha, that's our general equation. So if you substitute in a negative, then it becomes x plus alpha if alpha is a negative. So I found my factor. Now, obviously, I'm not a big fan of trial and error. There is a quicker way to get there, and it's called the rational root theorem. Now, this is a lot of stuff happening here. I'm not expecting you to write it all. Basically, what this huge slab of writing is saying is that when we're looking at a particular polynomial like this, beta divides this, and alpha divides that number. So you're going to be looking at a particular bunch of combinations, but it's going to narrow down the numbers that you can pick when you're looking for a divisor. So say with that particular polynomial up there, I've got 2x cubed. So if I'm looking for a divisor for beta, I'm looking for one of the factors. I'm either having the possibility that beta could be positive or -1 and positive or -2. For alpha, with 3, I'm looking at positive or -1 and positive and -3. So the potential factors of both of those numbers for beta and alpha. So applying that to our next polynomial, p of x, we're applying our rational root theorem. So I wish they'd made alpha come first instead of beta, but beta is for the leading term, it divides the coefficient of the leading term. So for beta, I could have positive or -3 or positive or -1. For alpha, which is my last term, the constant on the end, I could have positive or -1 and positive or -5. Cool? Okay, so obviously you're going to have to try a bunch of different combinations for this particular example. So the one that works, and it is going to take a little bit of time when you've got a couple of combinations, I always recommend putting the combinations in your calculator so you're not doing it by hand every single time. So to do these kind of things in your calculator and to do it quickly, that's when you are defining your polynomial. And I know it seems pointless when I taught you that at the beginning of the year where you put it into your calculator and you define it and comes up with done. It's really going to come in handy here because you're going to have to try a couple of combinations and you don't want to have to type in this long polynomial every single time. You want to be able to type in p of your number and have it come up with your answer. If it's not 0, you do the next one. You don't want to type in that polynomial again and again and again. Methods is about speed. Okay, so looking at my answer book, the combination that's going to work for me is beta being, alpha being +5. So alpha is equal to +5 and beta being +3. That's the combination that the textbook tells me is going to give me 0. Again, it's going to take a bit of trial and error for you guys. So checking that by hand, p of -5/3. I'm going to substitute that into my equation. So 3 of -5/3 cubed plus 8 -5/3 squared plus 2 times -5/3 minus 5. Once I've typed that all into my calculator or done it by hand, I'm going to get 0. So that tells me that 3x minus 5 is a factor. Because remembering your beta goes out the front here for your linear factor and your alpha is that constant on the side. And if alpha was a negative, that would be plus your number. Okay, the final few. So we have some special cases. So usually when we look at these with quadratics, they are our difference of two squares. Obviously we can't use that because they're not squares, they're cubes. So these are the theories behind them. Please write these down. So when we have x cubed minus a cubed or x cubed plus a cubed, we can apply these particular, if we need particular theorems to factorize them. So obviously looking at this, I can use my factor theorem as well. If I was to substitute in p of 3, that would equal 0 because 3 cubed is 27. So I would be able to find my factor that way. You don't essentially need these, but they are quick ways to do it if you like formulas. So using my rule though, I'm going to use the rules. So I'm going to be using this top one because I've got an x cubed minus a cubed situation going on. So 27 is a cubed, which means that a by itself is obviously going to be 3 because 27 is 3 cubed. So to factorize, I'm going to have x minus 3. And then in my next bracket, I'm going to have x squared plus 3x plus 9. Following my rule. Wherever there's an a, I'm substituting in a 3. Pretty simple, nothing too complicated. And then I've got this rule over here. So I need to factorize 8x cubed plus 64. So when you were doing this, that 8 and 64, you need to find them as cubes. So what I'm going to do is I'm going to rewrite 8x cubed as 2x cubed because 2 cubed is 8. So when I write it like this, I'm not sure how much we remember our index laws, but when I expand it out, that cubed goes to both. Just as a quick reminder of our index laws. So writing it like this, I've got 2x cubed plus 4 cubed, which is 64. So I've written them as my cubed numbers. So then I can follow my theorem here. So the 2x is my x and the 4 is my a. So I've written 4 when I meant a. So the 4 is my a. So then I can follow my rule, and I'm going to be following my second rule because I've got a plus in the middle now. So I'm going to get 2x plus 4 in one bracket, and then I'm going to get 4x squared minus 8x plus 16. Not that different from your difference of two squares rules. There's just obviously another factor in there now.